Okay, I might regret this. I'm going to try to upload a video while I'm recording another one. That may or may not work, but we're going to give it a try and see if this one works. All right, so this is continuing on. We just talked about subtraction videos. I don't know why I told you guys that. You wouldn't have known if I hadn't told you. Anyway, next operation we can do is what we call resolve. We can resolve a vector. What that means is we can break a vector down into other vectors. Often x, y, and z components. What do we mean by that? Well, if I've got some force vector here, F, what I'm saying is I can break this into its components, its x component and its y component. And then if I take the sum of the x component of this vector F and its y component, if I add those two together, that gives me the total F vector, which you can see graphically here. If I start from the end of this vector, from the head of this vector, I add the y component, and I go from the tail of the x component out to the head of the y vector, just like we did back here with the triangle method of addition. Just like we did with the triangle method of addition. One vector, two vector, resultant is the sum between them. You see what I'm doing here. I'm doing the same thing when I resolve a vector. And so that's another operation we can do. And with that in mind then, what that gives us, that opens up a tool we can use. This idea that I can resolve vectors into its components or into sum of smaller pieces. This gives us two ways we can describe a vector. This is L2, page 3 of something. Two ways we can define a vector. Number one is by magnitude and direction. This is often what we will teach people in a Physics 1 class, how to define a vector, is by magnitude and direction. So if I have some resultant vector here, and if I plot it in an xy plane where I draw the resultant originating from the origin, x0, y0, then I can define this vector by what we call its magnitude, which sometimes we just simply write as r without a hat. If r is a vector, if I draw r without a hat, that means it's not a vector. That's a scalar quantity. This is only the magnitude of that r vector. It's only its length. How big is it? What is the quantity of it? That's r. Its direction, we could use a common way to define direction is to measure the angle counterclockwise from positive x. And remember in lecture 1 where I threw a big fit and I said theta is not always measured counterclockwise from the positive x-axis. This is the reason why most people will struggle with that, is that often they were taught to always measure, to follow this standard protocol, right, where they measure theta counterclockwise in the positive x direction. And then what you can do is, a common way you can write this is you can say, well, the r vector then would be its magnitude, and you can write angle theta here. And if you write it in this way, what you're saying is this is the amount, this is the magnitude, this is the length, and this is its direction if I measure the angle to that vector counterclockwise from the positive x-axis. It's a very standard way of writing magnitude and direction of a vector. That's perfectly fine. The other way we can do that, in two ways to define a vector. The other one is to resolve the vector into x and y, and if you're in 3 dimensions, z, components. And then what you can do is, as we have drawn earlier, where you draw your r vector, your force vector, whatever it might be, and you can say, well, that is the sum of its x and its y components. Where this r is equal to the sum of rx and ry. And again, how do you find the magnitude? Well, the magnitude of r, which again we just say is r, is equal to the square root of the magnitude of rx squared and the magnitude of ry squared. And if I have z, I add rz out there also. We'll start doing some three-dimensional stuff as we go along in this course. But this gets us started for now. I'd reference Paul Harvey if I thought it wouldn't say how old I am, and say page 4 on my notes, but now it's only page 3 here on what we're drawing up. That's okay. I digress. Unit vectors. I asked some students one time, what is the first rule of Fight Club? And I got crickets, and I felt old. I didn't like it. I'm not old. But anyway, I digress again. Unit vectors. A unit vector is a vector with a magnitude of 1. The number 1. What happens if I multiply something by 1? It doesn't change it. You get the same thing. What happens if I multiply by a vector with a magnitude of 1? Well, I don't change the magnitude of my vector, but what I do is I preserve the direction of this vector. So a unit vector is one such that if I take the magnitude of this vector, I will find it's 1. This is normally how I draw 1, because you can see I do a terrible job drawing it fancy. For example, if I've got some quantity, some magnitude a, and I multiply it by some unit vector. By the way, my u's I'll normally put my lowercase u's I'll put a little tail on them. Some students have had thermo with me, and you know this. What happens then is I get a vector a, and you can subscript it with a little u just to indicate what direction it's actually in. Now, where this really comes in handy is in the x, y, and z directions. We use the I unit vector, the j unit vector, and the k unit vector, respectively. What does that mean? Well, you see what we did earlier. We said, well, I can take r, and r can be the combination of rx and ry vectors. I could also write it this way and say, well, that r vector I described earlier, I could describe as the magnitude of r in the x direction multiplied by the I vector, plus the magnitude of the vector in the y direction times the j vector. because the I vector is the unit vector in the x direction. The j vector is a unit vector in the y direction. I could add to it plus rz in the k direction, and that would be perfectly fine too, even if rz is 0. If it's two-dimensional, rz is simply 0. Right? So, in 3 dimensions, as alluded to, we'll work with 3 dimensions quite a bit. A common way to draw 3 dimensions, we're going to talk about right-hand rule. A very common way, if I've got a grid paper, I'll draw a z in the vertical. I cross my lowercase z's so they don't look like 2's. My y direction, if I can, I like to draw my y direction positive y in going to the left. To the right. Negative y to the left. Negative z down. X really represents into and out of the page. Into and out of the page, but you can't draw it that way, so I draw it kind of off at an angle here. And what we're saying here is if I were to draw the I vector, that would be here at x is equal to 1. The j vector would be here, j, at y is equal to 1. And the k vector, of course, would be pointing straight up here at z is equal to 1. That would be my k vector. Not the best drawing. Hopefully you get the basic idea. You're going to see a lot more three-dimensional stuff. So if it's like, Steve, I don't quite get that, that's okay. We're going to get there. L3. This is page 4 of something. Okay. Oh, I have an example. Time for an example. I'm going to stop here. And we'll work an example, because I've got a couple of examples. So I'm going to break the videos up. I'm going to stop here and put the examples in a different set of videos. So anybody watching it, if you stumble across my videos, if you're looking specifically for examples, I'd like to separate them out when I can. So that's what we're going to do here. All right.